Modern artificial intelligence relies on massive, centralized intelligence. Models are trained and deployed inside hyperscale server clusters, and every consumer device is merely a terminal asking the cloud for an answer. This centralization dictates the software we use. Standard machine learning frameworks like PyTorch and JAX rely heavily on sprawling Python ecosystems and proprietary CUDA toolchains designed for data centers. Pushing these specific frameworks directly to local edge devices triggers three distinct points of failure. First, embedding a standard Python ML runtime creates massive binary bloat, frequently exceeding 2 gigabytes. Second, converting models to lightweight formats requires lossy offline translation chains. Third, the networks are forced to operate as rigid, one-dimensional directed acyclic graphs. The experimental 0.83 release of the Layered Omni Architecture Open Fluke Machine, or Loom, presents a counter-architecture. Engineered entirely in Go, it operates as a deterministic neural virtual machine without a single external dependency. Shrinking an execution framework to a single 10-megabyte deterministic binary allows developers to embed models directly into mobile apps, web browsers, or game engines. Artificial intelligence transitions from a rented cloud utility into a sovereign, offline software component. Executing high-performance machine learning in Go traditionally hits the CGO boundary. Standard Go frameworks wrap external C++ compute libraries to process tensor math. Doing so injects a 200 nanosecond context switching penalty every single time the runtime switches from the Go stack to the system stack. In a deep neural network, millions of these micro-latencies stack up. The context switching devastates tight inference loops and places severe, continuous pressure on the Go garbage collector. This diagram compares a standard inference graph with Loom's structural solution, the mPolyVTD engine. Instead of processing neural networks as a linear list of operations on the left, Loom conceptualizes the network as a physical, three-dimensional space on the right. Every layer receives a precise geometric address, utilizing Z, Y, X, and L coordinates. This enables nonlinear data routing. Signals can bypass adjacent layers entirely, execute spatial hopping via remote links, and mimic a biological routing of cortical columns in a human brain. The core objective of the 0.83 experimental release is pushing this architecture further. It introduces three specific hardware acceleration paths: SIMD, metal, and NPU offloading, while ensuring the deterministic 3D execution remains perfectly intact. Conceptualizing a neural network as a physical, navigable space rather than a strict sequential order eliminates the standard bottlenecks of data routing and prepares the model for direct hardware integration. The first acceleration vector bypasses the CGO overhead entirely by translating auto-vectorized intrinsic logic directly into native Plan 9 assembly. Loom executes highly parallel mathematics straight on the CPU registers across both ARM and x86 architectures. This dashboard displays the empirical CPU benchmarks for the 0.83 release under intense stress. Looking at the highly complex Swiglu 3x3x3 volumetric grid and multi-ed attention blocks, the raw SIMD implementation yields latency reductions of up to 74% compared to standard tiled execution. The engine relies on multi-numerical polymorphism. Individual layers morph their precision dynamically at runtime across 21 distinct numerical types without requiring the entire network to be recompiled. Moving down to extreme sub-byte quantizations like int4, ternary, and 1-bit binary formats, the benchmark confirms exact mathematical parity. The engine maintains zero mathematical drift across dozens of live training epochs. Notice the processing times for these extreme formats. A 1-bit binary payload shrinks the on-disk serialization footprint by over 98%, dropping from megabytes to kilobytes. Yet its processing time slightly trails standard float32 execution. The CPU must expend overhead to unpack those densely packed bits into wider SIMD registers before it can execute the math. Executing raw native SIMD guarantees bit-exact mathematical fidelity. By packaging low-bit representations directly into the native runtime, developers can execute localized, quantization-aware training at the absolute edge. The second vector targets unified memory. In a traditional discrete GPU setup, transferring a multi-gigabyte tensor payload between the CPU's primary RAM and the GPU's isolated video RAM forces the data through a severe PCIe bandwidth bottleneck. The math processors on the graphics card sit idle, waiting for the data to arrive across the bus. Memory bandwidth, not compute capability, becomes the defining limit of inference speed. Apple's Unified Memory Architecture, or UMA, solves this. The CPU, the GPU, and the neural engine all share a single physical pool of memory with massive bandwidth. This schematic details Loom's web GPU backend, which maps directly to the underlying metal framework. Because the resources reside in shared memory, the CPU writes directly into a block, and the GPU reads it instantaneously from the exact same location.
This is true zero-copy execution. Furthermore, Apple Silicon provides hardware-level support for half-precision floats. By utilizing F16 math and custom metal flash attention kernels, Loom immediately halves the memory footprint of the key-value cache during the prefill phase. When deploying deep context windows on memory-constrained devices like iOS or visionOS headsets, zero-copy execution is a strict operational requirement to prevent system memory overallocation. The final vector addresses vendor-specific hardware offloading, specifically targeting the Qualcomm Hexagon neural processing units found on modern Snapdragon devices. Loom handles this via a vendor-agnostic C-ABI interface. During initialization, an operation called sync to accel passes the wait bytes to the accelerator's compiler, permanently baking them into the execution graph. From then on, steady-state forward passes require nothing more than memory pointer updates, bypassing the latency of continuous wait transfers. But hardware NPUs rely on dynamic hardware-level quantization approximations to achieve their speed. This relaxed mathematics breaks exact determinism. To classify this variance, the laboratory established the drift spectrum. It tracks output parity against the deterministic CPU bedrock across 6 categories: exact bit-perfect parity, indis for acceptable industrial parity, low bit, noticeable drift, severe H-drift, and finally, fatal logic failures. Evaluating 150 unique layer configurations reveals the cost of acceleration. While repeating inference natively within the Qualcomm neural network is perfectly stable, translating from Loom's deterministic Go engine into the NPU induces minor indis or low-bit drift for the vast majority of layers. The forward timing metrics reveal exactly when this trade-off is worth it. In highly fragmented, small-dimensional networks, the initialization overhead of the hardware accelerator becomes a severe liability. Testing a small-tier matrix operation with a batch of 4 and a dimension of 32, the Loom CPU completes the math in 0.009 milliseconds. The NPU takes 0.585 milliseconds. In this environment, the dedicated hardware operates at 1/50th the speed of the CPU. This graph plots matrix dimensionality against processing speed to find the architectural crossing point. As the matrices scale up toward large-tier operations, the limitations of CPU registers taper off, and the NPU's vast parallel architecture takes over. At a batch size of 8 and a dimension of 1024, the hardware accelerator achieves a decisive 7.0 times speedup over the Go CPU. However, this raw speed incurs an immediate mathematical penalty. That large matrix multiplication produces a 6.33 E-1 deviation, firmly categorized as high drift. The scaling law is clear. Vendor NPUs are unparalleled for accelerating massive, monolithic matrix operations. But for the highly fragmented spatial 3D grids composed of rapid microlayers, the Purabo SIMD CPU dispatch yields superior speed and exact mathematical fidelity. Current edge deployment follows a rigid lifecycle. A model is trained on a massive data center cluster, compressed, and deployed as a static inference graph. Once it reaches the consumer device, it is a frozen brain. It cannot learn new behaviors without a centralized retraining phase. Loom uses neural target propagation to unfreeze the model. A static inference graph sits beside an actively adapting 3D grid. Instead of crushing global backpropagation, target propagation computes localized states. Nodes use gap-based Hebbian learning to autonomously align to targets, maintaining stability. Researchers authoring architectures in Stern and Python can use an ingestion pipeline called planet bridging. It serializes active neural weights and streams them directly into Loom over a local TCP connection, rebuilding the mathematical graph as a highly compressed binary without offline conversion drift. Localized gap-based target propagation allows models to update their weights on the device based on real-time user interactions.
continually adapting without triggering catastrophic forgetting or requiring communication with a cloud server. Moving beyond static inference, Loom natively supports an embedded DNA engine. Using topological data analysis, populations of models mutate and evolve their exact physical structures based entirely on environmental feedback. We see this executing inside SQLite, an air-gapped simulation platform. Here, low-poly virtual entities actively learn emotional sentiment from user inputs and update their localized weights, operating in total isolation using embedded models. Developers embed this lightweight engine to drive dynamic non-player characters or run distributed physics simulations across secure, offline defense networks. By successfully merging a zero-dependency runtime with precise hardware offloading across CPU, unified memory, and NPUs, Loom 0.83 operates as the SQLite of artificial intelligence. It permanently empowers localized, sovereign intelligence at the extreme edge.